Have you ever been annoyed at how your fan oscillates from side to side? Why can't it just know where you are and point there instead? I made a system to do just that, but along the way ended up measuring distance using the speed of light, making a Rube Goldberg machine of electronics and software, and just generally sweating through an Australian heatwave. To start it all off, the fan. You can either aim it perfectly at you, but it becomes useless as soon as you move, or you can get it to oscillate, and then you have to chase it as it moves side to side. When I started this project, I thought to myself, how hard would it be to actually get it to point at me all the time? Should just be a quick project. It wouldn't take too long. Now, I can hear you asking, why would you even care about a fan? This is 2025. We have air conditioning. Well, let me tell you, my workshop has a severe case of wall deficiency, and like dads around the world say, I'm not paying to cool down the planet. Back to the project at hand. There are a few methods that we could use to make this. Number one, computer vision. Using a camera to point the fan at me using face recognition. The pro is, off-the-shelf libraries can probably just detect a face, and it wouldn't be too hard to keep a face centered in the frame. The con is, it really requires line of sight, because a camera. And I want the fan to really follow me wherever I am in the workshop, not just pointing at me. Number two, I could use ultrasonics. I could have, say, a tag on me that is emitting an ultrasonic noise and get the fan to have microphones that are always pointing to that source of the noise. Number three, I could use human presence detection. There are off-the-shelf sensors that give you an XY coordinate and like an angle, but where's the fun in that? Just buying something and integrating into a system. Then we get to the fun stuff. Ultra-wideband radio. Literally magic. Lets you find the distance between two radios by using the speed of light. The pro is, it's accurate to within about 10 centimeters once you calibrate it. And it has more applications than just a fan, which means more projects in the future using this. The con is, I guess, it's difficult to make and it requires maths, so that's everybody's favorite subject. Through an exhaustive decision-making process, I decided to choose the most difficult, but in my opinion, the coolest method, ultra-wideband. If you have any options me and my cat didn't consider, let me know in the comments. I'll explain in detail later, but through this radio, we can measure the distance between it and another radio to within about 10 centimeters. It's similar technology to how an AirTag lets you know how far away it is, or how your keys know that you're inside the car to actually let you start it. I didn't pay the Apple tax, so I only get the distance and not the angle. I designed a board that holds the special ultra-wideband radio and an ESP32 for Wi-Fi. I also added a compass and an accelerometer for good measure, future projects. And after making sure to include the prerequisite amount of mistakes that every prototype needs, I sent the boards off to be manufactured by this video's sponsor, JLC PCB. After exporting the boards from KiCad, it's easy to upload them to JLC PCB and get them to do the hard yards of assembly if you're lazy, like me. After just a few days, I got 10 of these boards sent halfway across the world, and they made sure to make them exactly as I asked, mistakes and all. You may notice that these don't have the super special radio that I've been yapping on about. Well, it turns out to mount them, you actually need them in stock, so if you're making a project with special parts like this, make sure to pre-order them. Thankfully, in my infinite wisdom, I made sure to order some when I was testing, as sacrifices at the altar of magic smoke. Thanks again to JLC PCB for sponsoring this video. Did anyone tell you that hardware is hard? And it turns out that I made a grand total of 5 major mistakes when I made this board. 4 of them almost killed the entire project. Number 4 will shock you. I missed 3 critical wires to the special radio: reset, a data line, and the interrupt pin. So I had to add bodge wires to make these wireless connection wired.
Connected successfully.
Yes, I'm counting each of these wires as a mistake. Number 2, the entire power supply was miswired and ended up killing 2 boards before I actually realized. So I just ended up stripping out the entire power supply and replaced it with a bog standard regulator, instead of the fancy buck converter that I already had there. Number 3, the compass just does not work. I haven't figured out why, and I still haven't fixed it. So after fixing this on every board that was still working, I had 6 working boards, 1 spare, and 1 other one that I accidentally killed in an unrelated soldering accident. So why 6 boards? 1 for me, 1 for the fan, and 4 are scattered around the workshop. So it turns out that in 3 dimensions, 4 distances are the bare minimum to uniquely find a location in 3D space. As a rule of thumb for those in higher dimensions, you need 1 more distance than dimensions to actually find a unique pointed space. Now, say we have 1 fixed radio. Let's call this an anchor. And we have 1 mobile radio with unknown coordinates. Let's call this one a tag. We have the distance between the 2. but no other information. That means that the tag has to exist on some point on a sphere around the anchors. And since 3D screens died out in the 2010s and we all have 2D screens, I'm going to have to make this a circle. And if we have two anchors that know the distance to this tag, we can draw another circle from the second anchor and reduce the possible points down to 2. This is where the solution circles cross. Adding one more anchor for this 2D example means that we can isolate down to a single location. Now, the fun hasn't stopped yet though. There are a bunch of measurement errors that we have to account for. Mainly, there's that 10 centimeter measurement inaccuracy that's inherent in the actual hardware itself, as well as differences between each of the different pieces of hardware. That means that one radio can measure one distance, but if you put another radio in that position, it can measure a slightly different distance. Now, I could do it properly and calibrate for each of the hardware differences and remove everything but the 10 centimeter inaccuracy. The radio even has options for that, but I'd rather not. So I just throw a bunch of maths at it to figure it out. Going back to 3 anchors, 1 tag, if we zoom in on that solution that we found earlier, we see that the circles don't actually cross. That's our measurement error, or in this case, also our calibration error. As it stands, our system is impossible to solve exactly. Plugging in the equation for spheres or circles, you won't get a number that pops out. There'll be no solution. But what we can do is minimize the errors and find the point that is closest to all the circles that we think our tag is on. Specifically, I use the Levenberg-Marquardt algorithm, and I'm sorry if I butchered the name, but any flavor of nonlinear least squares regressions will do in this case. Scale up our example one more dimension to 3D and add another anchor, and we have my workshop. I added my 4 anchors to the corners of my workshop, which, after figuring out exactly where the anchors are, roughly, lets me figure out the coordinates of the tags in my shop. Now that we can actually figure out the coordinates to the tag that is on the fan and on me, calculating the angle that the fan needs to point to is actually pretty simple. You just plug in some simple trig using the fan's coordinates and my coordinates, and then you get the angle that the fan needs to point to from the positive y-axis, which is this direction. And after months of work, countless mistakes, and a lot of sweat and tears, here's the moment we've been waiting for. A fan that follows me wherever I go. That is great. That's amazing. Not the most responsive, but it works. So this is my amazing following fan. I don't know if I'm gonna call it that, but it just follows me. It follows this, and if I walk around, it should automatically recalculate and point it out. It's the dumbest cool thing I've ever made. It's a fan. It's a fan. So now that you've seen the what, I'd like to show you the how. All the bits that I actually split it over, literally. This is the more technical part of the video for those that are interested. And if you are interested in these kinds of projects, consider subscribing, and I'll do more stuff like this. So, what exactly is ultra-wideband? How does it work? Ultra-wideband means that the bandwidth that this radio can transmit on is actually, well, ultra-wide. Wi-Fi channels, for example, are 20 megahertz. 2.4 gigahertz, 20 megahertz, you can add them together and get up to, I think, 80 megahertz. While the channel width of this is 500 megahertz. You can go all the way up to 1.5 gigahertz. And if you look at the wave shapes for a narrow band, it kind of looks like a sinusoid, while ultra-wideband just looks like a pulse. This pulse actually gives us a very defined leading edge, for lack of a better term. So we can, if we send a single pulse, we can accurately determine when that transmission actually starts. And since these have a really fast inbuilt timer, 64 gigahertz, you know, just casually inbuilt into the DW1000 that I've used here, you can literally measure the time that that pulse takes to go from one tag to another, and light moves about this far in that time. So 64 gigahertz, I think that's 15 picoseconds. But like with all engineering, there's always another problem. The 64 gigahertz timer in these aren't synchronized, so this might be counting, say, from 100, where another one could be at 1 billion, but they do increase at about the same rate. And thankfully, it is a radio, and it can transmit information. If we can transmit data between those, we can actually like synchronize them roughly, or at least figure out the amount that the count has increased in the time that it's taken. I'll explain. We use what's called two-way ranging, where we send 3 packets between these radios to measure the distance. An advertising packet from the tag to say, I'm ready and listening. An initiation packet from the anchor telling the tag the anchor's address and to initiate ranging. And then a response from the tag to the anchor that contains the time actually taken to process the packet and respond. Using this, the anchor can then compare how much time has passed since it started ranging, and then taking away the processing time on the tag and halving it, you can get the time of flight of light between the two radios. There is actually some extra compensation that takes into account. It's called asymmetric two-way ranging, but this is just the basic concept. And I'll leave a link in to the application note for this radio to see how it specifically works. How does the tag actually know what anchors to talk to? So like I mentioned with the two-way ranging, the tags actually send an advertising packet to each of the anchors, but I've modified the protocol a little bit just because the examples that were given rely on the tags being pre-programmed exactly with what anchors are known, and that didn't exactly seem to scale. I don't want to have to reprogram the tags in order to get them to, like, if I want to add another anchor or if I want to move things around. So instead, I've actually made it so both the tags and the anchors both advertise their addresses. The anchors just set a special byte to say, I'm an anchor, and the tags spend some time listening every minute or so to listen for those anchor advertising. So instead of just being a normal advertising blink, it actually sends a targeted advertising blink. So this one can say, I'm blinking, but I want to talk specifically to that anchor. So when the anchor realizes that the tag wants to talk to it, it initiates that two-way ranging that we were talking about. And then the tag can just iterate through each of the anchors that it's learned about. So since we have two tags, how do we actually handle packet collisions? And if you've done any networking or RF, you'll know that packet collisions aren't an if question, but a when question. And to mitigate this, I've just used the bog standard aloha method, which is literally just send it, and if it's not acknowledged, wait a random time and try again. So I've applied this to both advertising and ranging, so that anchors will advertise randomly between 3 to 6 seconds. So worst case, the anchors will need to listen to for 6 seconds to get the addresses of all the anchors, which isn't very long, and the battery life on these is actually pretty good, so I'm not too worried. And the tags will perform a ranging session, which is where it finds out its distance to each of the anchors every second or so. How is actually all the calculation done? Since I'm just using the ESP32, I'm using MQTT to send that data to my Home Assistant instance. You probably saw me using Node-RED at one point. So when the anchor starts up, it will send some data to Home Assistant with its address. It'll make a new device with a random sensor. It'll be its temperature, I think. Anchors will request XYZ coordinates, so I can write where they are in 3D space. Tags and anchors will have a slightly different version of software installed. The tag, specifically the one attached to the fan, will have special software on it specifically to drive the motor. Actually getting it to rotate the minimum distance to turn in the angle that I wanted was a little bit more annoying than I thought it would be. And the rest is kind of automatic when ranging occurs. This does the advertising, but the anchors get the actual distance and they never report back to the tag. They will instead send the data to Home Assistant, masquerading as the tag to say that this tag has this distance to that anchor. So in Home Assistant, when you look at the tag, you can actually see a list of all of the distances from each of the anchors. And then Node-RED just has a flow that when distance changes, it will calculate the coordinates in 3D space, and then it also has another flow. So then when the coordinates change, it will calculate the angle from the fan to the user tag. I'll have all this code on GitHub if you're interested in looking into it, although I guess that Node-RED flows are a bit hard to export. I'll figure out a way. And yeah, I guess people are going to be asking, why do this? This is useless. Who doesn't want a magic fan? Like, it's actually pretty insane having it follow you around the workshop. It's like not that useful because sometimes it gets to like 40 plus degrees out here. And either way, it's not just about cooling. I can now track exactly where this tag is to within like a space like this big. So if I have other systems in place, like I can have it turn on my mill when I walk to it, or if I have the dust collector on and I'm at my table saw, I can open up the blast gate for that, or the jointer or something. I mean, I don't have those, but I can definitely do it in the future. Yeah, if you have ideas, let me know in the comments, and hopefully I can get around to making a video about them. Otherwise, yeah, I just love to hear from you, and let me know what you think. I'll see you next time.